Hello and welcome to today's lesson looking at the topic of electrostatics, which is found in the GCSE course for physics in the electricity topic. So in today's lesson, what we're going to be doing is we're going to be looking at understanding the process of electrostatics. So for successful, and we learn in this particular lesson, we can understand the basic definitions of electrostatics, understand the rules that govern electrostatics, and look at the applications of electrostatics in the real world, which falls into the following part of the AQA physics specification in the electricity topic, which is the static charge section. Now, just to note, this concept is separate science only. So this topic we're going to look at today is not found in a combined science specification. So, electricity and electrical energies can have many forms in the real world, such as electricity in circuits, electricity in the mains, and also electrostatics. So in today's lesson, we're going to look at electrostatics, and we can experience electrostatics in many different forms in the world. But what is electrostatics? What causes electrostatics? And what rules govern electrostatics and detail how it works? Now, electricity is not only found in power lines and electronics made by humans, but it's also found in nature. Electricity is all around us, and the electricity found in nature is commonly called electrostatics, and we can observe electrostatics all around us, okay, in many different situations. Now, a common example of electrostatics, it can actually be lightning. Now, in these situations, such as the one shown previously, a natural potential difference, a potential difference which has just occurred naturally, causes a current to flow as electrostatics. So in previous lessons, we've considered the movement of electrons in a current. We know a current is a flow of electrons in a particular direction. So to produce an electrical current, you need to produce or induce a potential difference over your conductor in an electrical circuit. Now, an induced potential difference can include batteries or the mains power supply. But if electrons move with a natural potential difference, not a human-made potential difference, the current flown in this situation is leading to the principle of electrostatics. Now, a natural potential difference can include an imbalance of electrons on an object. So when electrons move in a current under no induced potential difference, only natural potential difference, this produces electrostatic electricity. Now, in these situations, this takes place when charges are not free to move, when they're placed on insulating materials, because over time, charge can build up on insulating materials, which can lead to a natural potential difference being developed between the insulator and its surroundings, and eventually the charge can move across materials, leading to a spark or a shock. Now, to understand how electrostatics work in detail, we must examine this property of charge. Now, electrical charge is a property of a particle which determines whether it moves in a current or not. So, for example, an electron has a negative charge. And so charge is a property that is due to the behavior an object exhibits. So all negatively charged particles repel other negatively charged particles, and all negatively charged particles attract positively charged particles, and all charged particles move in a current if a potential difference is placed across them in an electrical circuit. So a proton is a particle with a positive charge. So all positively charged particles repel other positively charged particles, whilst all positively charged particles attract negatively charged particles. Now, in theory, all charged particles move in a current if there's a potential difference placed upon them. But protons have this opportunity to move, but tend not to because they are so massive for a particle. Compared to electrons, they contain so much more mass, so it's a lot harder to move them, which is why protons do not move in electrostatics, only the electrons move. Not because they lack a charge, but rather they have so much mass it's difficult to move that charge. So, when considering electrostatics, the only charged particle or charge which moves between materials is the electron. Protons do not move at any point. So, charged particles can affect each other. So, what happens when two particles of the same charge are near each other, and why? Well, the two charged particles would repel each other, they'd move away from each other, because objects with the same charge repel each other, so there's a force of repulsion exerted on each particle. this is an example of the electrostatic force. Whilst if two particles of the opposite charge are near each other, what happens? Well, those two charged particles would attract each other, they move towards each other, because particles of opposite charge attract each other. There's a force of attraction between the two charged particles, which is another example of the electrostatic force. Now, the electrostatic force is what we call a non-contact force. This means the objects do not have to be touching each other to exert a force on each other. So those two charged objects do not have to be touching each other to exert that electrostatic force. Other examples of non-contact forces include the gravitational force and the magnetic force. Now, for example, the Earth and the Sun are not touching each other, yet there's a gravitational force of attraction between them. This shows that gravitation is a non-contact force. Conversely, some forces do need to be in contact with each other to exist. We call these contact forces. So examples include friction, reaction, and tension. So when two objects move across each other, the bumps on the surface of each object rub against each other, which produces friction. For example, when an object is pushed on a surface, to stop the object from falling through the surface, there is a force exerted upwards, which is called the reaction force, and if an object is pulling down on a cable, that causes a cable to stretch out, that's called the tension or tensile forces. So all forces can either be contact forces, which are forces produced when objects are physically touching, such as friction, air resistance, tension, the normal force, or they can be non-contact forces. Forces produced when objects can be physically separated, which include the gravitational force, the electrostatic force, and the magnetic force. But how do we represent the region of space over which non-contact forces act? Well, we do this by drawing something called fields in physics. So a field is a region of space where a body can feel a force. So for example, the Earth's gravitational field is a region of space where you can experience the Earth's gravitational force, and we represent fields with field lines. Now, examples of fields in physics include gravitational fields, such as this one, the gravitational field of the Earth. Now, the strength of the field is given by its field density. How many field lines are found in an area? So in a field, the closer you are to the object, the denser the field lines are, the stronger the non-contact force. Now, another example could be a magnetic field. Now, in this situation, we actually call magnetic field lines magnetic flux, and we measure that in Webers. Now, in a field like this one, the closer you are to the magnet, the denser the field lines are, the stronger the non-contact force. So from looking at this part of our magnetic field diagram, you'll notice the field lines are closest together at the poles, so the strongest part of the magnetic field is at the poles. And the strength of a field is given by what we call its field line or flux density. So the magnetic flux density, which is measured in Teslas, tells you how strong a magnet is. Now, in today's lesson, we're going to not look at gravitational or magnetic fields, we're going to look at electrical fields. Now, any charged object produces and is affected by an electrical field. So, for example, the electron, being negatively charged, produces an electrical field. Now, we draw field lines as straight lines from the object with arrows on them showing their direction. Now remember, any charged object inside the electrical field of the particle will experience the electrical force. The objects do not have to be touching. Now, we draw the direction of the field lines as the direction that a positively charged particle would take if it was in the field. Now, in a negatively charged particle, a positively charged particle is always attracted to the negative. So the field lines are always pointed towards the particle for a negatively charged particle. But for a positively charged particle, another positively charged particle would move away from it because same charges repel. So therefore, in all positively charged particles, the field lines point away from the object. Okay, now how close the field lines are together, the density of the field lines shows how strong the electrical force is. So the denser the field lines, the stronger the force is. So as you'll notice, we're closer to the charged object, the field lines are closer together, there's a stronger force. Now, all charged objects produce electrical fields, and we represent these electrical fields with field lines. And as you know, the field lines show the path a positively charged object on the line would take. Now, in the human, macroscopic, everyday world, we don't notice electrical fields of individual particles. That only occurs on the microscopic world. Instead, we observe certain behavior caused by charged objects on a large scale, which leads to the principle of electrostatics. So we've gone from the microscopic field line version to the macroscopic everyday version of electrostatics, which leads us to forming some rules which govern how charged objects behave. So we'll have a look at these situations. So charge can build up on certain insulating material. This occurs as electrons either accumulate on a material or leave a material. This produces a potential difference between the material and its surroundings, and if the potential difference is large enough, the charge can move across materials, producing a spark or a shock. Okay, now, when electrons move in a current due to a natural potential difference, this produces static electricity, and so natural potential difference is produced by moving electrons around due to friction, objects rubbing together. And we've got 5 rules to look at this. Rule 1, electrons repel each other as they want to get away from each other as quickly as possible. So electrons repel each other because they've got the same charge, and same charges repel each other. Okay, rule number 2. When there's no induced potential difference, the electrons want to go to the Earth as quickly as possible. This allows the electrons to move away from each other as quickly as possible. This is called earthing a charge. Rule 3. Only electrons move in electricity. Adding electrons to an object creates a negative charge. Removing electrons from an object creates a positive charge. Protons do not move. Okay, they've got too much mass. Rule 4. Electrons travel in conductors and do not move in insulators. Okay, so conductors can transfer this potential difference quickly, but insulators can store a large amount of potential because the charge is stuck in these insulators. And then finally, when the negative charge gets very large on an object, the repulsion between the electrons gets so large, it must go to the Earth, it must go to the ground. The electrons travel across the air, which forms a spark. The spark from the cloud to the ground is called lightning. Now, if there's a difference in the charge between the objects, we've got a potential difference. This occurs when there's a difference of charge. So the Earth has a potential of 0 volts, and all charged objects have a potential difference with the Earth. So potential difference leads to current flowing, it leads to charge moving. So let's just recap that. Electrons repel each other as they are the same charge. They want to get away from each other as quickly as possible. Rule 2. When there's no induced potential difference, electrons want to go to the Earth. Rule 3. Only electrons move in electricity. Adding electrons to an object creates a negative charge. Removing electrons from an object creates a positive charge. Rule number 4. Electrons travel in conductors and do not move in insulators. And finally, rule 5. When the negative charge gets very large on an object, the potential difference between the object and the surroundings is very large. The electrons travel across the air. This is a spark. So, the principle of electrostatics can only apply to charged objects. Okay, so charged objects are objects which produce an electrostatic field and are objects which interact with electrostatic fields of other objects. An example of a charged atom, a charged particle, is an ion. An ion is an atom with a different number of protons compared to electrons. The protons and the electrons will then be unbalanced, giving an overall charge to the object. So there's 2 types of ion. A negative ion, which is an ion produced when electrons are added to an atom, and a positive ion, which is an ion produced when electrons are removed from an atom. So the process of turning an atom into an ion is called ionization, and that tends to be caused by a collision of an atom with an energetic particle or radiation. So particles or radiation which can cause ionization could be electrons, something called photons, gamma rays, X-rays, alpha particles, beta particles. And these particles or radiation which cause this, we say, are ionizing forms of particles or radiation. So all charged objects obey the principle of electrostatics. Atoms with a differing amount of protons and electrons are called ions. Negative ions are produced by adding more electrons to an atom. Positive ions are produced by removing electrons from an atom, and the process of making ions is called ionization. This occurs when ionizing radiation collides with atoms. Now, there are many different applications of electrostatics in the real world. One of the most commonly thought of ideas is lightning strikes. So let's think about the following. What is lightning? Well, lightning is when clouds rub together in the sky, they transfer electrons between each other. This creates charged clouds. And when the potential difference between the clouds and the electrons is very large, the electrons travel to the Earth. That's a lightning strike. Now, in a lightning storm, why is it bad to be stood in an open space? Well, the electrons want to get to the Earth as quickly as possible because it's got a potential of 0 volts. So they will go through you as there's no other objects to travel through because electrons will always travel through Earth conductors faster than gases, so it's bad to be out there. Now, it's also bad to be stood under a tree because the tree is tall and in the ground, so it's earthed, so it's very likely to be hit by the lightning as the electrons want to go to the Earth as soon as possible. So the tree will either set on fire or conduct the charge to you. Okay, either way, not very nice. And why is it good to be sat in a car? Well, the car is made of a metal, a conductor, so if the lightning hits this, the electrons will move through the conductor as it can move faster through an earth conductor and not the human. It goes straight to the ground. You are left unharmed. So let's just clarify that. When clouds rub together in the sky, they transfer electrons, which creates charged clouds. When the potential difference between the clouds and the Earth is very large, the electrons travel to the Earth. That's a lightning strike. Now remember, there will be a natural potential difference because the Earth is always at 0 volts. So this potential difference will be reduced because the clouds are now charged. So this potential difference causes the electrons to move, so the electrons move to the ground. And the movement of electrons to the ground is a lightning strike. Now, the electrons wish to move to the ground because the ground is at 0 volts, and so the electrons can spread out. This means there's a lower repulsive force between the electrons in the Earth. Now, electrons want to get to the ground as quickly as possible, so they'll travel through a human as there's no other objects to travel through, and electrons always travel quicker through Earth conductors. I mean, it could also go through a tree, so because it will want to go through that Earth conductor, so the tree would either set on fire or conduct a charge to you if you were under the tree, so either way, not very nice. But if you were in a car, it would actually go through the metal of the car, because the metal is a very, very good conductor, so the electrons will go through the conductor as it can move faster through there because there's less resistance. It would ignore the human in the car and go straight to the ground, so you'd be left unharmed. So the car is acting as what we call a Faraday cage and providing a path of least resistance for the electrons to travel in. So a Faraday cage is the best way to prevent electrocution. Now, we can also create statically charged objects, okay, in school labs, because what we can do is insulating materials can gain a static charge if they're rubbed against each other. The frictional force provides the energy, the work done, for the electrons to move from one object to another object. So when insulating materials are rubbed, electrons leave one object, so it becomes positively charged, and then the electrons will go to another object, which will become negatively charged. So if we rub a perspex rod with a dry cloth, the perspex rods become positive because the electrons leave the perspex rod and go to the dry cloth. Now, the energy needed to move the electrons comes from the energy produced by the frictional forces. So work is being done by friction. But if you rub the polythene rod, the electrons will travel from the cloth to the polythene rod, so the polythene rod will become negatively charged. So the only particles which move in static electricity are electrons. Protons do not move. Now, negatively charged electrons are rubbed off one material and onto another. But when objects rub to form static charge, the sizes of the positive and negative charges are the same size. So if one has a positive charge of +3, the other would have a negative charge of -3. You've always got to have equal charges when you rub two objects to charge them. So when one material gains electrons, it becomes negatively charged, and the material that loses electrons is left with an equal positive charge. Now, as we said before, this idea is it is a non-contact force. So static charge is an example of a non-contact force, as the objects do not have to touch for the force to be exerted, same as gravity. So remember, the electrical field must be present, because if the objects have their electrical fields, that means they can produce an electrostatic force between the objects without them touching, which means that two negatively charged objects could in fact repel each other, two positively charged objects could repel each other, and a positive and negative could attract each other without actually touching. So, a static charge can be generated by rubbing insulated objects together. The friction provides the work to move the electrons. So when electrons move onto an object, it is negatively charged. So polythene rods become negatively charged when rubbed, and the cloth becomes positively charged. But when electrons move off an object, it is positively charged. So acetate or perspex rods become positively charged when rubbed, and the cloth becomes negatively charged. So let's summarize what we've learned in today's lesson. Certain insulating materials become charged when rubbed together. Electrons are transferred when objects become charged. Insulating materials that become positively charged when rubbed lose electrons. Insulating materials that become negatively charged when rubbed together gain electrons. And like charges repel, opposite charges attract. So if we've learned in today's lesson, we understand the basic definition of electrostatics, understand the rules that govern electrostatics, and we've looked at some applications of electrostatics in the real world. I hope you've enjoyed this lesson on electrostatics and have a lovely day.